Hello community, today we code a data pipeline in PyG, in PyTorch Geometric, and I want to show you how easy it is to construct data for your graph neural network. So here we start. PyG is easy. A graph is used to model a pairwise relation, this is visualized by edges, between our objects. We call those object nodes. And a single graph in PyG is described by an instance of, and we have torch geometric data.data. And this holds the following attributes. Now you have to remember three of them. The first is .x. This is the node feature matrix, which has a particular shape. It has at first position the number of nodes in your graph, and second, the number of node features. The edge index, I will show you in a second, shows you in a particular shape, 2 is the default value, the number of edges. And the third one is .edge attribute. This is more or less the edge feature matrix. Sometimes we call it attribute, or sometimes we call it a feature, either of a node or an edge. Both can have feature matrices. And the particular shape is, at first position, the number of edges, in the second position, the number of edge features. Beautiful. And then, of course, we have to have a target against we train. And this is either a graph level or node level ground truth labels. They can have arbitrarily shapes. Beautiful. So here we go. This is our first install. Yeah, I need some sentence transformer in the later half, but let's install them. We are here on a Colab notebook. And then we go, of course, we import Torch. And we install here, as you can see, PyTorch geometric.git. This will take some seconds, but this is the way you can very easily install PyG on a public Colab notebook. You see CUDA Core 113. Beautiful. We need some libraries then, of course, from PyG. We need a specific data set. We need some data where we have some homogeneous data graphs or some heterogeneous data, some download, extract, we transform. We need this too. And then, of course, we have our pandas and our sentence transformers we both know and love. Great. So at first, an easy example, just to show you how the easiest case is, we build a graph with 3 nodes. Beautiful. Now, at first, our x and then our edge index. You are familiar with this too. X is easy since we are operating in PyTorch. We have a torch tensor. We want to have 3 nodes, so we say, for example, -1, 0, and 1, easiest case. Each node contains exactly 1 feature. And then we have 4 edges. Now with 4 edges, you will find out these are in case edge from node 0 to 1, from 1 to 0, so more or less the reverse, from the node 1 to the node 2, and from the node 2 to the node 1. So beautiful, we have 4 edges, and then we construct our data, our object, torch geometric data.data, x equals x, unbelievable, now you're amazed. And our edge index is our edge index we just defined over here. So now you can have a lot of analysis on this. The first, the node feature matrix. What's the look of the tensor? Well, unsurprisingly, it is -1, 0, and 1. Edge index, well, it's exactly our input. Edge attribute we did not define, so it would be nothing. And then you can have a look at the object itself. And now this is a typical representation you should be familiar with to tell you the data. There's a specific form. This is our node feature tensor and our edge index. Normally you would have then the edge attribution and so on, but this is the minimum configuration. Beautiful. Remember the .x, our node feature matrix with the shape, the number of nodes, 3 here, and the number of node features. I told you we have only 1 feature per node. Beautiful. Now you can have a look. If you're not familiar and you get a data set, you can have .keys that shows you exactly what you have in your data set, the edge index and x. or you go with what are the number of nodes, dot num nodes 3, the number of edges, in our case 4. Does it have self loops? No, we have no self loops defined. Is it directed? No, because we defined from 1 to 2 and from 2 to 1. So we have an undirected graph. Beautiful. If you want to accelerate this, you put it on your GPU, torch.device CUDA, and you can run it on a GPU. Beautiful. Now, all of this are, of course, the classical task from graph neural network is semi-supervised node classification. This means you have your graph, you have your data, but some of your nodes are missing a specific label. And your task is now to deduct from the specific labeled nodes and their neighbors and the structure of the graph from the missing nodes that are not labeled, what is their classification, what is their label. Beautiful, let's do this. We have a Cora dataset. Showed you in my last video, a Cora dataset is a beautiful dataset of scientific documents, exactly 2,708 scientific publications. We call this now nodes. We have a citation reference between the authors in the scientific papers, so we have defined 10,500 edges. And as I showed you in my last time, the feature vector, or the feature tensor to be correct, is a 1,433 dimensional feature tensor, a feature vector. Beautiful. This is it. When we have 7 classes, let's say physics, mathematics, chemistry, bio, whatever. And from some of the nodes, we have a missing classification, and you have to find the classification for each and every of our 2,708 nodes. Beautiful. Told you everything. Beautiful. How do we do this? You will say, hey, why 1,433 features? How is it possible? Easy. I'll just show you, if you're not familiar, how to construct a vector out of a document. Now, the easiest thing that we know is scikit-learn. And as you can see here, we have the feature extraction, and we import 2 beautiful things. We have a count vectorizer and a typical TF-IDF vectorizer. Now, first case, we have a certain text passage. This is a rhetoric example of a quantum foam, happy elongated here. So it would be correctly 2 sentences, but we just say this is our sentence 1 and our sentence 2. And let's say this is the whole text that we have. So easy. You have now your count vectorizer from scikit-learn. You say, I want an anagram just from 1 to 1. Eliminate my typical English stop words like hello, me, you, too. We put in our sentence 1, our sentence 2 into the count vectorization, and we have an output. Let us have a look at this. What it does is, this is a typical English stop word, and is a typical English stop word, so these words do not show up. But otherwise here, all the words show up that are not English stop words. And then here you have for the sentence 1, this is our sentence 1 here. And you see a 0 tells you, where's a 0? Gangsters. Has a 0 in the first row. And it tells you gangster is not a word that is within sentence 1. Gangster is a word that is within sentence 2, as you can verify here. And you see here, sentence 1, 0, and in sentence 1, we have here, yes, 1, gangster is available. So you can now go through 1,000 sentences, sort this, make a beautiful sequence out of this. This is all done for you by your TF-IDF vectorizer. And you have suddenly created from a sentence, remember here, this is your sentence 1. Now you have a new representation for learning. This is sentence 1 in numerical values, if you have a specific dictionary, vocabulary. And this vocabulary tells you exactly which word is or happens in a specific sentence. Beautiful. Now you know how to create a 1,433 dimensional bag of words feature vector for each node when the word is a scientific document. Beautiful. Done. Okay. Now we import Cora to show you the whole number of nodes and everything. So here we go. Number of features in Core is 1433. This is our typical presentation. We have x 2708 nodes. The dimension is 1433 from the feature vectors. We have, by the index of the edges, we have 10,000 edges, 500 edges. We train against 2708. We have the training, the test, and the validation. The splitting of our data, we are familiar from our ML models. The number of nodes, the number of edges, the node degree, the number of training nodes that we have. You have no isolated nodes, so everything is connected with an edge somehow. You have no self loops. This is false, and it is undirected. Beautiful. This is our data set. Now, if you want to have a look at the data set, this is always you get this specific data set we just talked about. Now, what is the kind of our node features? Of course, it is a tensor, because I told you that for each node we have a feature tensor. A node feature is always attached with a tensor attribution. So here we go. First sentence here would be this 1433 dimensional 0001001 something. We go through, and you know now what it is. It is a word vector constructed by, where is it? Bag of words. This is the simplest case that we have. And we use it here for our Cora example. Okay. This is it. Good. Here. Now, the size, this is easy. It tells us our tensor has 2708 nodes, and the dimensionality of the feature vector for each node is 1433. Edge index you are familiar with. This is now the tensor representation. The size is, of course, we have 10,556 edges. The number of node features is, and you tell me, it is 1433 dimensional feature vector, and the number of edge features we have 0. Beautiful. Now we have everything defined. Now we want to have a classification task, so we have 7 classes. Beautiful. And you can have a look how the distribution is from all the members in the class. So for the class 0 and for the class 6, you have 351 members, and class 6 is 180 member distributed. Beautiful. Now let's do the training on a GNN. No, stop at first. Easy. I show you how to code an MLP, a multi-layer perceptron with linear layers, before we switch to GCN layers. So what is the easiest case? Easy. We should be able to infer the category of a document solely based on its contents. This means its bag of words feature representation, our tensor, without taking any relational edge information into account. This means we do not care about the graph structure, who is connected to whom, who has cited whom, and we do not have now an adjacency matrix that will flow into our coding. Beautiful. So what is the way? This is easy. We have a linear layer in Torch. Great. We use this. And we construct our MLP, our multi-layer perceptron. Now we have two linear layers, as you see. First we have an input and a hidden channel, and then in the second layer, of course, we have as input our hidden channels, and then we have the output. We want to have a classification, the number of our classes. And the feed forward is easy. We have the first layer, we have a nonlinear ReLU function where we learn, we have a dropout, and the second layer is more or less our classification layer. And the model is simply defined with 16 hidden channels, and this is it. So you see our MLP model is linear and linear layer, 2 linear layers. Input, you have the 1433 dimensional feature vector. Then we have the output feature of linear layer number 1, the hidden channels. Now in linear layer number 2, we have now as an input the hidden layers, and as an output, we want to have a classification of 7 classes, and this is the easy MLP. Beautiful, beautiful, beautiful. So now let's train this model. What we need a model. And like in any other ML model, we need, of course, loss functionality. We have here the cross entropy loss already defined, and then we need an optimizer, and this is our typical Adam optimizer. You can give it a specific learning rate to start with, you can give it a weight decay function, beautiful, everything how you know it, and then you simply define a function where you say, hello, this is my training function, model.train with my optimizer, with my data. I have here my criterion is my cross entropy loss, and this is it. And of course we define here for the evaluation also not only the training function but also the test function, because we want to have a numerical value that we can evaluate the performance of our ML model on. And this is our evaluation data set. Beautiful. Number of epochs. Let's train this model. Yes, 200 done. Wow, very fast. And then let's calculate the numerical test accuracy. And we say, we are only at 59%. Now you can see this is rather bad, but why is it not better? And it is easy, because we have linear layers. So what do you expect, no? So the normal next step is we build a graph neural network from our MLP. So we easily convert our MLP linear layers now by swapping out the linear layers, and we insert PyG graph neural networks or graph convolutional network layers. And this is done in the GCN model. This is by Thomas Kipf. I have a specific video on GCN. You read here is explained in a video and showed in a video. Leave you the link in the description. Have a look if you're interested. But we now build our GCN model. Now, this looks absolutely familiar to you because we have two layers where input is again number of features. We have our hidden channels, input, output, and input. And we have the number of classes. And then we construct a feed forward where we have the first layer, we have a nonlinear ReLU function, we have a dropout, and our second layer, and we have 16 hidden channels. And you say, hey, this is absolutely the same. Yes, now you know why I showed you at first the MLP, because there is such a beautiful parallelity. So here we go. Our GCN model now has our graph convolution layer. Input, we have our 1403 dimensional feature vector. Output is the hidden layer. Hidden layer is the input to the second layer. And we have a classification problem to 7 classes. And we want to have one of the 7 classes as an output. This is it. Beautiful. Because we want to visualize something, we have just an helper function. And then what we say is, okay, here we go. We evaluate this model. Show me, before we train the model, where are the data? How is the data distribution? The different classes, are they clustered together? Are they free floating? Show me what I'm doing. So we have just the pure data and we visualize it. Yes, hello. Would be nice if you would start working today. And this is just a visual proof. Always check somehow visually about your data set. So you see, we have pure chaos. Beautiful. Maybe there's here a little bit orange dominating, but otherwise you see there's no correlation. Beautiful chaos. This is what we want. So great. So what do? We do the training and test functions. We have now our model, our GCN model we just built. Again, for an optimizer, we have our Adam optimizer with a defined learning rate and a weight decay. Please adjust accordingly. And we use the cross entropy loss. Beautiful. So again, absolutely the same. You have your model training, you have your output, your criteria, everything is there. You have the test for the evaluation. Yes, and we do the training. So let's train this model. 28, 70, 80, 90, 100. Beautiful. So what is now the numerical accuracy on our test data set? Hey, we increased our accuracy to 81%, so much better than in the 50s. Oh, this is great. And also we have now the visualization. Let's just check visually if it is also a clustering of our data noticeable, that we have the colors of our nodes now clustered in a color clustered visualization, just to make sure. It doesn't take long. And we will see if our model trained well. Of course, we have only 81%, so it is not perfectly color separated. But I would say it's not so bad. We have here the yellow. We have here clearly the green cluster. We have a little bit of the blue. Here the whatever ochre. Here orange, dark green, and here gray. So here we have a little bit of intermix, but for the training just in seconds, this looks very nice. So this is a successful training. Next video, because we are already 20 minutes in, I will show you the next step up in complexity, because we will use a more complex data pipeline, and the graph will also be more complex, but next one we have with multiple node types. So this is where it really gets interesting. This is the teaser for next time, and I hope I see you in the next video.